In a circle, there are usually two types of angles. The first, and which I consider to be the easier type of angle, is the central angle. So let's first draw a circle here, because that's where all these angles will be located when we're learning about them. What is a central angle? A central angle is an angle in a circle whose vertex is located at the center of the circle. The arms of this angle then end up becoming radii of this circle, or radiuses, if you want to call them that. So for example, angle AOB here would be a central angle because its vertex is located in the middle of the circle. If another example, let me choose a different color, would be maybe this angle here, angle COD. This would also be a central angle because its vertex is located at the center of the circle. For now, let's give this angle AOB a value of theta, because we all love Greek symbols. And let's give this angle COD another value, maybe alpha. There we go. So a useful thing about central angles, well, actually, let's first go over this. You may notice that this angle AOB subtends an arc AB. And believe it or not, arcs are also measured in degrees. So what degree would this arc AB have? Well, it turns out that the degree of arc AB is equal to the degree of the central angle subtending the same arc. So in this case, the value of arc AB would be equal to theta, and the value of arc CD would be equal to alpha. So that's pretty neat. And this doesn't just work for the two angles I've drawn here. It actually works for any angle we choose to draw. For example, maybe a smaller one here. Let's call it E and F, two more letters. And if I can fit this here, beta, angle beta. The value of arc EF would still be equal to the value of its central angle. So central angles are great to work with. They have a pretty simple concept to understand. However, inscribed angles are more difficult to work with, as we'll soon see. So let's draw another circle here. Compared to central angles, the vertex of an inscribed angle is no longer located at the center. Instead, the vertex is located somewhere along the circumference of the circle. And if I can trace it out properly, that'd be great. But it's located anywhere on the circumference of the circle. So for example, let's make our vertex here. The arms, or the sides of this angle, are now chords that extend from this point to any other point on the circumference of the circle. So this would be an inscribed circle. Let's draw our points again. O is no longer our center, but it's a nice letter to use. And let's give this the value of theta again. Now, looking at this here, for inscribed angles, the value of arc AB is not equal to theta. It might be equal to this angle here, or actually it is equal to this angle shown here, the central angle subtending the arc, but it's not equal to theta. And it seems really obvious too, because obviously this angle up here does not look to be even remotely close to angle theta down here. And again, just like the central angles, the fact that the inscribed angle is not equal to the arc is true for any inscribed angle drawn in a circle. Oh, that's not straight. But for example, if we drew another inscribed angle here, maybe CD and alpha again, the measure of arc CD is still not equal to alpha. And we could get the lime color again. That's weird. But we could get the lime color again and draw another inscribed arc, and we'd find that it's not equal to the that the value of the inscribed angle and the arc it subtends, it's never equal. So while central angles might seem to give us a lot of information, it seems that inscribed angles are kind of useless, right? It seems like even if we knew the value of an inscribed angle, we wouldn't know the measure of the arc it's subtending. But actually, there's a nice theorem called the Inscribed Angle Theorem. Let me write it down here if I don't change to eraser all the time. Sorry, there's an Inscribed Angle Theorem. And what it basically tells us, let's draw another circle again. It's going to be a lot of circles in these first few videos, just a heads up. But what our inscribed angle theorem says is that for any inscribed angle, for example, our inscribed angle here is angle AOB, and its value is theta. The value of our inscribed angle is always, and I mean this always, equal to exactly 1/2 of the value of the central angle subtending the same arc. And this is always true. So, for example, well, actually, since there's more lines in this diagram, we're not going to draw too many, but it would also be true for an inscribed angle here, subtending the same arc. Let's call it alpha. Oh, I just realized we already have alpha. Sorry, alpha. Beta, much better. Now, according to our inscribed angle theorem, beta would also be equal to 1/2 of the central angle subtending the same arc. And if we notice these two statements that I've written down here, we can then say that theta is equal to beta, which is pretty neat. So now we've just learned two interesting things. One, that we can relate any inscribed angle to the central angle subtending the same arc. And two, that any two inscribed angles subtending the same arc are always equal, no matter where they are located on the circle. So, forgive me, I'm just going to draw one more inscribed angle. For example, even this inscribed angle here, oh, I wish that I could draw straight lines, but that'll have to do for now. But this angle here would still be equal to 1/2 of the central angle subtending the same arc, and would therefore be equal to any other inscribed angle subtending that arc as well. Now, it's always great to know these theorems, but what's even better is to know why they're true. And this is an important part of competitive geometry and even competitive math. But the thing about competitive geometry is that the questions often aren't single one-liners, and they often require lots of creativity. So therefore, let's say if you understood a proof, you could then use that proof to build an understanding and help gain new ideas, like think of any creative solutions to help solve problems. So first, or I guess now, that leads us to our proof of the inscribed angle theorem. And the proof for the inscribed angle theorem can be broken down into three cases. And once again, for each case we'll require a circle. Let's go over what the first case should be for now. Let's draw our diameter of the circle, or let's consider that our diameter. And let's say we had an inscribed angle here, and our central angle is here. We want to prove that the inscribed angle theorem is true, so theta equals 1/2 alpha, for when one of the arms of the chord is a diameter of the circle. So let's call this diameter AB. Our first case is when one of the arms of the inscribed angle forms the diameter of the circle. So let's prove this now. Let's add some more points, maybe C and D, and let's look at triangle DBC. Let's notice that angle CDB is a central angle. So therefore, these two arms, since they both are the radii of the circle, they must be equal. And if they're equal, it means that the triangle is isosceles. And if it's isosceles, it means that angle DBC must be equal to angle DCB. And if we see that, now that we know that these two triangles are isosceles, now that we know both angles of this triangle, we can solve for the last angle, CDB, by knowing that the sum of the angles of a triangle are 180 degrees. So angle CDB is equal to 180 minus 2 theta. Now, let's look at angle ADC. We notice that the diameter AB is a straight line, so therefore, angles ADC and CDB are supplementary and must equal 180 degrees. But we know the value of angle CDB is just 180 degrees minus 2 theta. And using simple algebra and maybe some better handwriting, we can see that angle ADC is simply equal to 180 degrees minus, in brackets, 180 degrees minus 2 theta, which is equal to 2 theta, as these ones cancel out. So we've just proved it for our first case here, which is great. Now, let's put C1 for case 1 to refer back to that. And now we go to C2. Let's draw the diameter of our circle again. Now, our second case for the inscribed angle theorem is when the arms or the sides of our inscribed angle don't form a diameter of the circle. For example, one arm of the angle may be here, and the other arm will not be this diameter. And what case 2 checks is when this other arm is on the other side of the diameter. So then the sides of the angle are on different sides of the diameter of the circle. Case 3 will examine when both arms are on the same side or on the same half of the circle, but we'll go into that later. So anyway, let's draw the center of our circle again, and let's create our central angle. We want to prove that this angle here, this whole angle called theta, which we can also call angle CBD, we want to prove that it is equal to 1/2 of the central angle COD. So let's write it here. We want to prove that angle CBD is equal to 1/2 of angle COD. And this is what we want to prove. We have not proven this yet. Now, if we look at this diameter drawn here, we can kind of break this up into 2 halves. Oh, let's just label angle COD alpha, by the way. But notice that we can sort of cut this into 2 halves. Maybe let's call angle ABD theta 1 and angle CBA theta 2. That one is a dot. And similarly, let's call angle AOD alpha 1. That's a theta. Let's call it alpha 1, and let's call angle COA alpha 2. Notice that if we can prove that angle ABD is equal to 1/2 of angle AOD, or if we can prove that theta 1 is equal to 1/2 of alpha 1, and if we can prove that theta 2 is equal to 1/2 of alpha 2, let's relabel alpha up here. If we can prove these two separate cases, so case 1, case 2, when we combine them together, if we know that theta 1 is equal to alpha 1 over 2, and we know that theta 2 is equal to alpha 2 over 2, then when we combine them, we get theta is equal to alpha over 2, just by adding them together. But if we look back to case 1, we can see that trying to prove alpha 1 equals alpha, trying to prove theta 1 equals alpha 1 over 2, and theta 2 equals alpha 2 over 2, it's basically just like proving our first case twice, which we have proven. So therefore, just by referring back to our first case, we can see that the second case must be true as well. So therefore, we have proven the fact that theta is equal to alpha over 2. I guess we should write it back down here. If angle ADC is equal to 2 theta, theta is equal to alpha over 2 as well. Now, let's go to our final case, which, if you remember before, it was when the arms of the chord, the arms of our inscribed angle were both located on one side of the diameter. So it looks like this. And it seems like this might be the hardest case out of the three. But it turns out that it's actually not too bad. But either way, let's draw all of our points again. Connect our central angle, which will be angle COD, and let's call this angle alpha. And instead, well, actually, yes, let's call this angle alpha. So angle COD equals alpha, and angle ABD, missing the A, but that's fine. Angle ABD is equal to theta. So theta is this angle here, ABD. Now, similar to case 2, let's divide theta into two parts. Angle ABC, which is equal to theta 1, and angle CBD, which is equal to theta 2. And theta 2. And for this proof, let's even create another angle, this angle here. Let's call it beta. So beta would be equal to angle AOC. So now that we have all of our values and all of our angles, let's try and use the previous cases to prove our third case, because that's always easy to refer to previous cases. So let's take the entire angle ABD, or theta. By the inscribed angle theorem, we can actually see that theta must therefore be equal to, or let's take a step back. We see that the inscribed angle ABD subtends arc AD, and so does the central angle, angle AOD. So theta is angle ABD, our inscribed angle, but our central angle AOD is actually equal to alpha plus beta. I wish my A's were good today, but can't be helped, I suppose. And by the inscribed angle theorem, we know that theta is equal to alpha plus beta over 2. And I might need some more space for this third case, but not to worry. It's still not terribly difficult. Oh, my screen moved. Hold on. And we're back. So we know that, actually we're not quite back because we can't see the circle anymore. But that ought to be good enough. So we know that theta is equal to alpha plus beta over 2. And this is one way, or this is one way we used our first case to kind of help us with our third case. But we can use our first case to help us again with theta 2. And we see that theta 2 is the inscribed angle ABC, and the central angle subtending the same arc is equal to angle AOC, which is B, or beta. And by the inscribed angle theorem, we know that theta 2 is equal to beta over 2, which makes sense. But since we know that theta is equal to theta 1 plus theta 2, we can rewrite our first expression here, down here, as theta 1 plus theta 2 is equal to alpha plus beta over 2. But since we know that theta 2 is already equal to beta over 2, we can subtract theta 2 and beta 2 from both sides of our equation to get theta 1 is equal to angle alpha over 2, which is exactly what we wanted to prove. We wanted to prove that the inscribed angle theorem worked even for an inscribed angle whose arms were on one side of the diameter only. So that's the angle we were trying to prove here. And we can see that obviously it must be true. So great. We have now just proved all cases of the inscribed angle theorem. And we can use it to solve any type of problem involving angles in a circle. So I guess before we finish off for this lesson today, I just want to do a few practice problems to help test your understanding. So let's draw a circle. Ooh, that's one of my better ones actually. Center here. And let's, oh, I didn't realize how wobbly these lines are. That's slightly better. It'll do for now. And let's say that we know this angle here is 78 degrees, and we know this angle is 29 degrees. Given this information, we want to find the value of theta, this angle here. And we know, and it might not be clear from this diagram, but let's say AD is a straight line. So how would we go about finding theta? Well, first, we could use our inscribed angle theorem. Since we know 78 degrees is the value of this central angle, it must therefore be 2 times the value of any inscribed angle subtending the same arc. If we look here, angle ABC is one of these inscribed angles subtending the same arc as angle A, that's missing a O, angle AOC, our central arc. So therefore, let's cover this up better. Therefore, the value of this angle here must be equal to 78 over 2. Maybe a brighter blue would be better. But it's equal to 78 over 2, which is equal to 39 degrees. And using the fact that the sum of the angles of a triangle are 180 degrees, we can simply find that angle BDA is equal to 180 degrees minus 39 degrees minus 29 degrees, which is equal to 112 degrees, I believe. It's always good to confirm. These are the points on math contests you don't want to lose, especially when you're at the home stretch. So you can pretend this is 30, 40. Yeah, it's 112 degrees. So great. This would help us solve these kinds of problems where you've probably never learned anything like this in school, but it would help you solve problems on math contests. Now, let's do one last problem and one last circle. So let's draw this here. And this here. And we know this is 50 degrees. And what is the value of this angle? And this might look like a very tricky problem because our inscribed angle theorem, if you remember, it requires us to know the value of a central angle. But there is no central angle here. We're not given the value of any central angle. So how are we supposed to know the value of theta? Well, our inscribed angle theorem tells us that for any, or I'll try to write it down, for any two inscribed angles subtending the same arc, I wish I wrote as fast as I spoke, but for any two inscribed angles subtending the same arc, their angle values are equal. And if you want a proof of this fact, just draw any two inscribed angles subtending an arc and give the central angle a value, and using that central angle, find the value of the two inscribed angles, and you'll see that they're always equal. And actually, I may have even included it in my original explanation of the inscribed angle theorem. But nevertheless, due to this fact, since this inscribed angle here and this inscribed angle, I'll use maybe red, and this inscribed angle here, since they are subtending the same arc, their values must therefore be equal, and therefore theta is equal to 50 degrees. And this is the end of our first lesson, which was an introduction into central and inscribed angles. Hopefully, this should give you a foundation of competitive geometry, and we can then use what we've learned during this lesson to apply to more complicated topics, including more angles, sometimes inside, sometimes outside of a circle, and hopefully it also raised your interest in competitive geometry and competitive math. So thanks for listening, and I'll see you guys next time.